Hi guys, welcome to video lecture number 1, Forces. In this video what I want to do is give you a more refined definition of what a force is, and I also want to give you a new set of vocabulary to describe forces that act on objects in everyday life. Go ahead and pause the video and record the essential question in your notes. Ever since elementary school, I'm sure that forces have been defined for you as a push or a pull. And that's a great starting place for defining what a force is. But we can go further. We can say that a force is a push or a pull that can change the motion of an object. More specifically, that can change the velocity of an object. And recall from the last unit, if you change an object's velocity, whether it's the object's speed that is changing or the direction that the object is traveling, you are accelerating that object. Acceleration is a change in velocity. So forces are a push or a pull that can accelerate objects. Forces, just like acceleration and velocity, are vector quantities. In other words, you can't describe a force unless you say how big it is, or what the magnitude of the force is, and in what direction the force is acting. You can't push or pull something without talking about what direction it is being pushed or pulled. Forces are measured in newtons, hence our picture of Sir Isaac Newton down here. And a newton is an interesting unit because the unit itself defines what it quantifies, what a force is. It's a derived unit. 1 newton of force can accelerate an object that is 1 kilogram by 1 meter per second squared. What does that mean? A kilogram of mass or weight is about the size of a big textbook. Think about a big, heavy textbook. That's about 1 kilogram, 2.2 pounds. If you want to accelerate that textbook by 1 meter per second squared, if you want to increase its speed by 1 meter per second every second, then you have to push it with a force of 1 newton. So a newton, capital N, describes how a mass is accelerated. And we can measure newtons using a spring scale, this little device down here. A spring scale is a simple device. It has a hook on one end, and if you pull on that hook, there's a spring inside the spring scale that shows you how much force you are pulling with. Now that we've defined what force is and we've looked at how we can measure forces, I want to give you or equip you with a vocabulary to talk about forces that you experience all the time. When most of us think of force, we instantly think of the force of gravity. And gravity is a unique force in that on the Earth, it accelerates everything at the same rate, at a rate of 10 meters per second squared. So it doesn't matter how much mass you have, if you're falling because the force of gravity is pulling on you, you accelerate at the same rate. If you fall for 1 second, you're falling at 10 meters per second. If you're falling for 2 seconds, your speed increases to 20 meters per second. After 3 seconds, you'll be traveling at 30 meters per second, so on and so forth. The reason gravity has a constant acceleration on any object is because the force of gravity depends on the mass of 2 objects and how close they are together. When you're on the surface of the Earth, your mass is inconsequential compared to the mass of the Earth. And the distance you are from the surface of the Earth is inconsequential compared to other distances that we've explored in our galaxy and in the universe. So the mass of the falling object and the distance it is from the Earth can kind of be taken out of account. And so everything accelerates at the same rate with gravity. This is not the case with most forces. Now, another force that you probably haven't heard of is called the normal force. The normal force is usually a force that counteracts gravity. It's provided by the surface that an object is resting on, and it's perpendicular to that surface. I can show you better than I can tell you. Some examples of normal force are illustrated here. In the first example, you have a box resting on a table, and this second arrow would be the force of gravity pulling the box towards the center of the Earth. And the reason the box isn't falling is that the table is providing a normal force, which is perpendicular to the table. Perpendicular would be an angle, a right angle of 90 degrees. So the normal force is always perpendicular to the surface the object is resting on. Now, if the same box is resting on an incline, the normal force remains perpendicular to that object, or to the surface that object is resting on. So if something's resting on an incline, even though gravity continues to pull straight down towards the center of the earth, the normal force doesn't counteract it completely. And so things on an incline tend to slide down because the force of gravity isn't completely counteracted by the normal force. All right, another type of force that you may or may not have heard of is called applied force. Applied force is a term that can be used for all kinds of forces that are acting on an object from an external source. And by external, I don't necessarily mean outside of, I mean caused by something. Let's take a look at some examples of applied forces. So an external source, if you want to move a box up a ramp, you must have an applied force. In this case, the force is applied by a human being. To make a car go, you need an applied force. The applied force is provided by the engine and the wheels or traction on the road. If you want to leave our atmosphere, you're going to have to get on one of these rockets. With the space shuttle, the applied force is provided by the boosters of the shuttle. One thing about applied force, as it's shown in this first diagram, tends to be in the direction that an object is moving. The applied force for the car will be in the direction of the car's movement. The applied force of the rocket boosters in this picture are in the direction that the rocket is traveling. So applied force tends to be a force that causes an object to move in a certain direction. One force you probably have heard of, but might have some misconceptions about, is centripetal force. Centripetal force is a force that causes an object to travel in a circular path. Remember in the first slide I said that forces can accelerate an object. Keep in mind that accelerating an object doesn't always mean making it go faster. If you force something to travel in a circular path, you are also accelerating that object. What I always think of with centripetal force is this guy right here, the good old playground merry-go-round. My kids love this because it's the most dangerous thing on the playground, and they know that when I push them around the merry-go-round, they're going to have to hang on for dear life. When they're hanging on, they're providing a centripetal force. Unless you hang on to these bars and pull yourself towards the center of that merry-go-round, you're going to go flying off. Centripetal force holds something in a circular path. Another great example is the force of gravity once again. Between the earth and the sun, or between the moon and the earth. The reason the earth orbits the sun is because gravity provides a centripetal force to keep it in that circular orbit. The reason the moon doesn't go flying off into space is because the force of gravity from the earth provides a centripetal force to hold it in a circular orbit. All right, so centripetal force and applied forces tend to make things move or accelerate in a certain way. The force of friction is a very important force that tends to oppose any motion, especially when we're talking about motion on the earth. There are lots of different types of friction: static friction, sliding friction, rolling friction, and fluid friction. Remember, fluids can be liquids or fluids can be gases. If you're moving through a liquid or if you're moving through a gas, the gas or liquid will resist your motion with what we call fluid friction. If you jump into a pool, for example, when you hit that water, it opposes your motion. And if you jump from very high up, you feel that friction, the force of that friction resisting your motion in a dramatic way. Some examples of sliding friction. If you try to slide a box up a ramp and the ramp is very rough, lots of sliding friction will occur. If the ramp is smooth, it's easier to push that box up the ramp. Rolling friction occurs between a wheel and a surface. So the smoother a road, the more rolling friction this car would provide. This rocket is experiencing fluid friction. As it goes through Earth's atmosphere, the atmosphere opposes its motion. So keep in mind that friction is a force that generally works against an applied force. Don't discount it. Friction can have some serious impact on how quickly an object accelerates, or if it accelerates at all. The last thing that I'd like us to be able to do is to represent the forces that are acting on an object by using a free body diagram. Let's imagine for a second that this car is on a road and it's traveling along. It's in motion. If I asked you to consider all of the different forces acting on this car, you would probably start by saying that gravity is pulling the car down towards the center of the Earth. We always remember gravity. Now that we have a new vocabulary, if this car is driving on the road and it is not falling towards the center of the Earth, we know that it's not doing that because of the normal force that the road provides. Now, this car is in motion. The engine turns the wheels, and the traction of the wheels against the road propel it forward. So let's draw a large arrow to represent the applied force, and we'll use subscript A for applied. Now, notice that the applied force is larger than the force of gravity or the force provided by the road, the normal force. When you're drawing a free body diagram, the size of the arrow represents the magnitude of the forces present. And often you can actually write out the actual amount of force that is being experienced in each direction. Now, if the car is driving on the road, it's going to experience friction. Friction opposes the forward motion of this car. So as the tires propel the car forward, a certain amount of friction is going to be experienced as well. So we'll include our force of friction. Now, it would be helpful to quantify the magnitude of each force, and we could do that by adding numbers, but for now, we'll just leave arrows in place. It's pretty apparent by the size of the arrows that even though this object is experiencing forces in 4 different directions, that the net force, or the sum of all the forces that it is experiencing, will be in the direction of the applied force. This car will be moving forward. Now, in many free body diagrams, instead of actually using an object or a picture of the object, you just get this box, okay? This box, drawn out, it could represent a car, like we just illustrated. It could represent a plane that's flying. Really, any object on a free body diagram is just represented by a box and by the different forces that it is experiencing at any given moment in time. Thanks for watching.